then they went to DC. They keep promising a map version. I don't think they've done it. See, we were talking about the sign rank box, and that's really fun. Any questions on the Wilcoxon, sign rank Wilcoxon?
In the Sonic Wilcoxon, there's this really elaborate scheme you have for kind of deciding what to do when two ranks are kind of, what you think would have the same rank. I'm curious from an asymptotic standpoint, does that actually matter at all? And if I were to just ignore what you do, kind of the rules of thumb, would it affect the asymptotic distribution? Or would it still be the solution? And these different things kind of arbitrary. Yeah, don't worry about it. Maybe I'm phrasing this question poorly.
The sign rank Wilcoxon, you rank the absolute deviations from low to high. If you have ties, you split them. If you do have ties, it remains distribution free, and I don't think we'll pay too much mind in this class. R does it automatically. It adjusts for the ties. There's a variance.
Yeah, that's what I was asking.
Again, it's the one sample problem. Everything else, everything stays the same. You're testing the median. Whatever. Specificity is. The average rank is plus 1/2. You expect half of them to be positive. Okay, then it's asymptotic. Now, if you have a lot of ties, then you should adjust the variance. And if you think about ties, if you have ties, okay, then you take like the average of the ranks, we reduce the variation. It's like you're moving, you have these observations. So you're testing, getting to 10, and the observations are deviations will be left. So we usually split the ranks 1 and 2, right? So you assign each of these 1.5 row. And this we rank 3. This we rank 4. Then you've lost some variation. If you didn't have to do this splitting, you would have 1, 2, 3, and 4, and there's more variation in these numbers than there is in these numbers. So there's lots of variation. Okay. So I don't think I have it in my notes, but there's a formula for ties where you adjust the variance. What happens if you have ties? The mean's okay. The null mean's still okay. this value is still okay, but you have to adjust the variance. But it's an adjustment down, so your test statistic becomes bigger, right? Your standardized test statistic will become bigger. So if you don't make any adjustment, it's conservative. So I don't mind not adjusting in this class. I think Minicap probably does too. I know R does. They make calculus. Another thing, if one of these observations were 10, then we would throw it out. Start with the sign. But then, for the confidence interval or the estimate, you use all of that. You use it. So, any more questions on sign rate? We talked about estimation. It was the identity that gave it away. We just had to note the T plus is also the number of positive Walsh averages. And based on that, the estimate is the median of the Walsh averages, and you can pick off the confidence interval the same way as you get to this. Is there any questions on this? The estimate's the median of the Walsh averages, right? And then the confidence interval is just those ordered Walsh averages. Where the C value you see is different than the sign value. See what now the problem with the Wilcoxon is you don't want to do this, right? The last thing you want to do is start making these tables. The number of Walsh averages is n times n plus 1 over 2. It's like a order n squared. So in this case, we have 7 data points, right? In that table, we have 28 Walsh averages. But it goes up like n squared, so you don't want to do that in practice. Actually, in the old days, before the age of computers, we would spend some time on some rules to define these things, but the computer can do it now, so we don't do it. Yeah, if you had to do one of these on a quiz or something, you know, do this nice. So let's talk about efficiency a little bit, and we need this anyways for precision. I mean, we have 3 procedures. We have the sign rank Wilcoxon, and we have the t-test. So I'll use one over the other. So we need to talk a little bit about efficiency. And we'll just measure efficiency based on, actually it's the asymptotic variance of the estimate. This would be the ARE, it's actually asymptotic. Relative efficiency. So it's the ratio of the asymptotic variances and the estimate. Okay. Well, you can do this, you can do it this way too, and that's the way to think about it. Just square the standard error, and it's the ratio of the standard errors, okay? Or the things that are actually estimated. So here we have these observations, right? There's some, in some population, we like this, and with the Wilcoxon, we do assume symmetry. So this would be the population. And then the density. Okay, this would be a sketch of the density, okay? Again, on half the areas here, on half the areas. Okay, then if you're doing a t-test, the estimate of x bar and the variance of x bar is the variance of the population over n. And you're probably used to that, right? Well, we've talked about variance. But it's not nice in terms of that, right? In terms of that, it's one of the variance is it's that error. I'm not assuming any calculus in this course. The integral would be the area under the curve. The curve here only is x minus v squared comes after that. That's not nice. There's nothing nice about that. I can give you. We talked a little bit about the logistic distribution, and if you want to find the variance of the logistic, you end up with an infinite series. So at times, we just want to. Okay, so then we have the sign test. Here are the estimates of the median, right? We're using that symbol. Well, no, we're using that. And then what's the variance of theta? Well, this is that tau we talked about divided by n. And then what's tau? Tau is 2 times f left to be population. Okay? And then the ARE, let's do the ARE then between theta hat and x bar. Just the ratio of the variances, and the ends always cancel out, so it's just sigma squared over tau sub s. Now, what is that? It's a horrible formula, right? And let's just look at the normal, because the normal is really the punchline of this whole thing. I mean, why would you go to a sign rank when you can just use the mean? The sign is. Why do we complicate life? And the reason we complicate life is this ratio at the normal. Okay? Now the ARE depends on the population. It's not distribution free, that's for sure. And so, but it is a ratio of variances. So for the population, you only have to know the form. It doesn't matter what the mean is or what the variance is. So the population is normal, and the form is the standard norm. So let's look at this population. Normal, and the form. Oh, actually, it's this. There's the density, right? It's still not that nice. And then for this, I need the variance. The variance will be 1, right? This is just a standard normal. And then I need 1 over 2 median is 0. You now have to square that. Right? So that would be 1 over 2. And then this is f of 0. 1 over the square root of 5. And then e to the 0 is 1, so that's what that is. So it's pi over back to 2. Okay. Then here's the punchline. So the ARE would be sigma squared over tau s squared. And that would be 1, and then you have to square this. Now, what does this say? Well, how do you read the ARE? You just look at the ratio. Sigma squared to tau sub s squared is like 0.63. So the sigma squared is 0.63 times tau sub s squared. And then your confidence intervals, if you use x bar as this, right, you might have a 0. I just use a 0. So which one would you want to use if you were sampling from a normal? Well, the variance of a normal, the variance is 0.63, okay? It'll be smaller. You have this down here, right? Well, I'm going to use the median, and I say, no, I don't want to use the median here because in this calculation, if you've calculated this, if you multiply this by the square root of 0.63, you'll get this one, okay? This one is much smaller. And you can see it directly too. The variance of x bar is 0.63 times the variance of the sample median. Just forget about the ends. You can put ends here, right? You can divide each of these by n. So you can either see it this way, or you can just go back to the formula and say the variance of x bar is 0.63 times the variance of the You wouldn't use the median, right? You would never use the median if you're sampling from a normal population. And a lot of applied people see this and they say, no, I'm not going to use the median. My data may not be normal, but it's not that far from me. Well, maybe you're a proponent of the median, right? And you can say, well, you're not sampling from a normal, you're sampling from a low exponential. So if you change the game a little bit and say, no, it's not normal, the population is low exponential with loss, and now the density looks like this. But then you can show that this ratio comes out to 2. You can add some math to show that from the screen. That's not the purpose of this class. But so if you're sampling from this distribution, then you definitely would use the median because the variance is twice variance of x bar is twice the variance of u. Is there any questions on that? See, if it's normal, that's the story. Never use the median. You're out of your mind if you use a median. If it's Laplace, this is the story, and you're out of your mind if you use x bar. You're going to lose precision. Right? Any questions on that? Something to think about if you've never seen it before, but you should have a reason, right? I can give you an uncountable number of methods. All right. Okay. Well, before we do anything, then let's talk about the sine rank Wilcox, and it comes along, and what's its ratio? Well, the variance of theta hat by the is tau squared. I could put a W here. What is this thing? The population. Horrible mess. I don't know if you get an idea that maybe it's more akin to x bar than it is to the median because of an average. It is an expected value. The actual expected value of what it does. And then one in the population, one of them. And then you can show that sigma squared, this thing squared, it's 3/4. Which is roughly 0.95. That's why we have Wilcox, because sigma squared is better at the normal. You cannot beat x bar. Okay, it's a normal population. But the variance, the ratios only at this fraction. See, that's a lot bigger than that. Right? The median is this. It's 0.63, not 0.954. So you don't lose much if you use Hodge's number. So that's why we discussed it. Now what if it's not normal? Well, if the tails are heavier than normal, then usually the Hodge's name it doesn't beat the sign here. Going back to the normal punchline is you use 5% efficiency. If you use sine wave Wilcox rather than X bar at the normal height. Okay. Now, this will hold for the two sample problem and for the regression and for the linear models we look at as well. So we'd never have to come back and say this. The last thing I want to point out on it is a distribution which is very close to normal in ways, but which will always, generally have outliers. And it's the contaminated normal distribution. And for the contaminated normal distribution, your sampling is usually from a good population. But then once you get these outliers, and some people think that's the way real data is, I'm not sure. Anyway, you're sampling X, but X is, most of the time it'll be, you can, again, form is the only thing that's important here. So most of the time it's a standard normal. This is your observation. Epsilon is usually small, like 5%. So 95% of the time, that this would be it's just a Bernoulli random variable. If epsilon is 0.05, then 95% of the time, the data is coming from the standard normal form, okay? And 5% of the time, it's coming from a standard normal, but it's hit by sigma sub c, which is contaminated. Like epsilon to the 0.05, actually, in that table I'm going to show you, sigma C is only 3. Now if epsilon is 0, then it's just standard normal. And you've got the efficiencies, right? Then in the table I'm going to put up here, we just have epsilon drifts through some values. Okay. And then we look at this efficiency. You can see that. This is with epsilon equal to 0. This would be standard normal, and this is the efficiency of the Wilcoxon with respect to least with X bar. Okay, this is theta hat HL, and this is X bar. And this is the median back here. This is theta hat. So at the standard normal, the efficiency of the median is 0.63, and the efficiency of the Frank Wilcoxon is 0.955. Now we just have 1% contamination. That means 1 out of 100 times we get a bad observation on the average. X-bar certainly beats the median, but it loses to the cyanide Wilcoxon. So it only need 1% contamination, and the Wilcoxon is 1. Okay. If you get 3% contamination, it's about the same story, but it's one more. And then you have to go to 10% contamination until you get X-bar and median about the same. This is 0 to 3 places. And there the Wilcoxon is 1.4 times. You go to 15% contamination, that's 1.5 times. Any questions on that? I don't know, maybe it doesn't motivate us to get the Wilcoxon.
What book is that one?
This book only cost $100. It's cheap. It's written by Tom. So he just spent $100. Oh, yeah, that was okay. So what I'd like to do now is go to the 2 sample problem. Any questions on 1 sample problem? Now, computation is not a problem, right? If you're on Minitab, you can do next task instant, the median. And if you're on R does not have a sign test. If you find a sign test on R, let me know. I have to write my own this morning. Do something else. Oh, yes. So that's not the moment. It's probably one. And then W test, right? Went. The Wilcoxon, median, right? Lemon. R is just Wilcox. Dot on the test. X is right. And then make sure the confidence interval is turned on. Usually has some false. And of course the t-test. In Minitab it is this t-test. Intent. R is t-test. I don't know if this is on or not. So computation is no problem, right? So you can go either way.
Is that Wilcox part of the standard R, or do you have to
like
download it? Okay.
The sign isn't. I thought for sure there was a sign test. I don't know why I thought that. I can put one up on the web. Just clear it out there. I have it. Okay? then let's talk about two-sample problem. Now, two-sample problem, we have two samples, okay? There's a couple of two-sample problems. The one is when we're going to do that, where the samples are independent of one another. And then there's the paired design. Right? We'll talk about that later. Later. So we have a sample of X in this one. From one population to population one, and then sample of Y's, making different sizes from other populations. So behind the wall, you have two populations. And, they could have the same distribution, but that would just be like a wiggle room. That would be like an H0. Right? We don't really have two populations there, we just have one. We just think we do. That would be the natural null hypothesis, the populations are the same. And then, and this is a nice problem where they have about the same distributions. The one is just shifted up from the other. It's like a first order effect. Second moments are the same, but the first moments differ. This would just be a shift. Or they could be vastly different. They could be the same. They could. This is a nice one. This is called the location model. That's the one I'm picking on. This is the location model. Population distributions are the same. And here you get the same H0, but delta equals 0. These are exactly the same. We just have the assumption of location. Also, these could be the means, right? This delta is equal. I'm not going to put it down here. I'll just say equal. It's a difference in means. You read textbooks where they make a big deal that this is a difference in medians, but it's not. When you go to the location model, it's a difference in medians too. And they could be vastly different. And certainly the one we will talk about later will be where the scales. I mean, you might have some sort of a shift. But the scales differ too. Actually, these are the same. The delta's the same. So then we want to come back. We'll talk about that problem. Now, when the scales do differ like this, then I don't know if you want to test location. A lot of people still do, okay? I'm always puzzled why they want to test location if the scales differ vastly. Right? It's like they're missing the point. And the one has a lot less noise. Why are you worried about the means? But people do, and we'll talk about non-parametric tests as well. What's a non-parametric test? Non-parametric test is really neat. For this example, so we look at the location model. case, you might want to, you could say theta of x. We can't actually make it a model. We can, so we can let z sub I equal x. Z and 1 plus 1. J. Y. We have two samples, but for a moment we can put them right into a nice little model if we just define the first batch of z's to be the x's, the second batch of z's to be the y's. And then we can write the location of this. And then we have c sub I equals 0. And this is c and 1 plus j. So I have two, right? Z's and c's. Then I can write it this way. We don't have to make a big deal about this now, but when we go to regression, we just have a regression model. It's like the rest of the course is regression. It's just from different points of view, right? That's not quite true. This is a regression model. See, if I is between 1 and n1, then this is 0, this is gone. And actually the error is, I think the error is xi. And then for the later batch of z's, the c's are all 1. So it's delta plus e sub I. So I can just put e sub I like this. Here's my e's, right? And what are your x's? There's your e's, right? And then I just have to add the alpha to get the 1s. Medians don't have to have a median 0, they'll have median theta x, right? We'll be using this quite a bit, so we get used to, I think we'll get used to it. If you want to, for today, we have a batch of x's and a batch of y's. Okay. And if you were in your simple elementary class, you would say, you would take what? The mean of the x's and the mean of the y's, compare them, that's your estimate of delta. Okay. Your test statistic would be the mean of the x's minus the mean of the y's, or vice versa. And you might have to standardize it. In this case, the non-parametric procedure is very simple. You just throw them all together, you rank them from low to high, and then you add up the ranks to y's. And this is something called Mann-Whitney. We combine the x's and y's. And then low high. W with the sum of the ranks. Okay? You could take the sum of the ranks of the x's too, it doesn't matter. You'll get the same p. Maybe we should have a j in here because we're using j. Doesn't matter. Now, if you go back to this picture, that's actually what's going on. Again, this would be an HA picture, right? Rho is greater than 0. Y is picked it up. And this test is going to work, right? Because when you sample your x's will come in here, and your y's will come in here. There might be some overlap, but generally the y's will beat the x's. Okay. And so they'll get the high ranks. Let's just take a huge data set. Here's my x's. And here's my y's. Now you just combine them and rank them. If they're pre-sorted like these are, it's easy to do. I wouldn't do anything. I would just put the ranks above with circles. So you're just combining them and ranking them. And the 18 comes before 25. So does the 22. And so does the 24. And then here's the next one. Right? Then here's one. And then this is 9 and 10. And then if you got ties, then you just take the average of the ranks. Okay, so our W here would be 4 plus 5, that's 9, 15, 24, 34. I'm writing this thing down. Okay. And then what do you expect W to be under H0? Well, you combine the data and rank them, right? The average rank would be n plus 1 over 2, where n is the sum of the sample sizes. And then how many y's do you have? You have n2 of them. So again, the mean is very intuitive. There's nothing hard about the mean. It's just the number of y's times the average rank. So in this case, I mean, we didn't pick the sum of sample size. Divided with 2. So you're on the upside, not by that much, right? Okay. So you at least need to add the variance. Here's the P, right? Oh, I'm sorry, we're testing values. So my P, I'm going to reject if W is too large. I observed 34, so my P value is this, right? Again, you might use a continuity correction. And so I'll just approximate your Z. In class, that's what we use, right? You just need something downstairs. And just like the sign rank, the variance is not that intuitive. So downstairs we have that. Which is about 5, right? So it's 6 over 5, so you're probably not going to reject. Definitely a p-value. We just want standard deviation. P-value would be about what? Probably between 16 and 20%. Okay. So that's an easy one. It's a very easy one. It's very intuitive. Right? Some books actually start with the two-sample problem because the procedures are so simple. It's except the scientists. Talk about the scientists. This is stressful. Let me see. I might not be able to get it. We had problems with this last one. Just make up some estimates. We have days. This is a real data set. It's LDL levels of cholesterol, and it's from an experiment up to many years ago. There's 2 treatments. The first set of quail were on placebo, and the second set of quail were on the treatment. It hopefully lowers LDL cholesterol. This is at the time of the big cholesterol race. It was a very big race in the pharmaceutical industry, right? You just think of how much money Pfizer made with Lipitor. They made billions, right? Billions of dollars. They won the race. Actually, Pfizer didn't invent Lipitor. I think it came out of Harley Davis. It's probably came out of Mark. Pfizer despised it. So rich. So it's interesting. Still the first Okay, so, let's just break the data sets, and we can do that. Often you have data stacked together like this, and then any tab command is straightforward, it's unstack. So you just unstack, I put the data in C2, those are the measurements, right? So I unstack. C2, let's put in like C5 and C6. You can name the columns and the subscripts and C1. So this would be the placebo. And this would be that's backwards. So, yeah, C6 is the placebo. So definitely a diagnostic for the two sample problem is the box plots, right? And the box plots are pretty informative here. You might worry a little bit about the scale, but we only had like 10 observations in this data set, so you've got to be careful. And there's definitely an outlier. That quail probably, maybe he didn't follow the diet. Okay. It was a designed experiment. We'll talk about designed experiments a little bit later, but this was a clinical design, so you can think of it this way. I think there are 20 and 10. I think there are 30 data points. And 20 were assigned to placebo, that's this group, and 10 were assigned to the treatment. And then the quail were fed separately, and the LDL, the active drug compound, was put in the diet. The other quail had the same diet, they just had a placebo. If there was any kind of delivery mechanism in the drug, they would have it minus the compound, right, whatever. And then after 6 weeks or whatever it was, their LDL cholesterol, low density lipids, was measured. Okay. And then you might want to test. So it was in what, C6? C6 or not? C6 should be larger. So the command is man. We just do the man. We can work on some. I think it's first column on the side. So find out. I just want to do one side. Data placebo on this data. Treatment. And then I'm testing number 0 versus parameter. The delta is positive. And this would say the LDL of a placebo the LDL in general is the LDL of a treated. Messed up. Don't get confused on the notation. It's a very simple problem. You just have to make sure you have your C6 before C5. Well, you know the answer, okay? So these are up more than these. So if your estimate comes out to be negative, you probably mix the columns. And there's delta hat on the first line is 14. So for the data, then this would be 14. So you reduced LDL by 14 units. For a long while, Upjohn had a drug in the competition it had. We were in the race.
How did you unstack? What was the command to unstack, and how did it choose between the?
I had the subscripts were in ones and zeros. Okay, they don't have to be ones and zeros; they just have to be distinct things. And then the measurements were in C2. And then you unstack C2, and then you have to give column numbers where you want the data to go.
So you do okay.
So this was my data, C1, C2. This was the treatment indicator. They were ones and zeros. One was referring to placebo, and the zeros were treated. And then C2 of my LDLs wrote well for 6 weeks. So I just did unstack C2, and then I need 2 columns. And the semicolon, the subcommand is subs. Subscripts are in C1. Sub means subscripts. Okay? And you can do that with clicking too. I think there's a way to click that. See that later. Notice the bad thing about the Minitab command is bad thing about this run is it takes forever for Doc King to work. Switch back and forth. It just gave you the value of the sum of the ranks. It didn't give you the standardized test statistic. I don't know why. And R does the same thing. So I'm always puzzled by that because what's 344? That means I have to compute these things and know what that means. I mean, mean in this case, I think there's 20 and 30. So mean would be 15 and a half divided by 2 would be 20. Yeah, it would be 300. It's over 300. 310. Yeah, 310. And we observed 344, so we're 34 up. Is that far enough? Well, you at least get 6. You just make sure you understand that. W came out to be 334. And then I have to do the Z myself. Again, I must back up with continuity correction. We got one, what,
Can we switch the dot cam?
we got 1.5. Awesome. What's the point estimate for the Van Whitney Wilcoxon? It's the analog of y bar minus x bar. And again, there's an identity here that's not obvious. But from that you can pick out the point estimate of the This is a very intuitive test statistic also because it's just a number of times y beats x. When I teach an elementary class, sometimes I just use this form of the test statistic. It's like every pairing between a y and an x is a match, and then you count the number of times y wins the match. Okay? The identity is this, that this W that we're looking at, this U could be 0. W is the sum of the ranks of the Y's. It can never be 0, right? The Y's can get all the low ranks, then, in fact, maybe put down the Where's the Y's getting all the low ranks? They get beaten each time. So U would be 0. And then the Y's can be all the high ranks. Again, the Van Whitney is sort of dense. It's not like a binomial. It's of order n squared, right? So you're going to have a lot of points where you have positive mass. It's not so discrete. And from this right here, you can tell me what the constant is. So this would be 2 times n plus 1 minus that. It's not obvious, but this algebraically just comes down to this. And then, of course, you say yes as soon as you see that because there are n1 times n2 matches, and half the time, if the null is true, half the time y should be x, and half the time x should be y. So the expected value u should be n1 times n2 over 2. Okay? So now tell me what the point estimate is. I'll just write this expression. And my test statistic is u of 0, right? And this is what I have to solve. So you've got to pick delta hat, so how many differences are greater than delta hat? n1 times n2 over 2. And then how many are less? So it would be n1 times n2 over 2. So the other half's what? It's just the median of the differences, right? It works. It'll work. It's all the same equation. If I take the other half, the median. Then we solve that equation. So that's your estimation. Now, we haven't talked about a sign procedure, but we will. And if you just commit to that, I should say, I'll say the high schooler. High school algebra. The mean of the difference is the difference in the medians. That would be actually the sign that you can't do that. That's the estimate, then the confidence interval is straightforward, okay? You just order those differences. I'll give you a cutoff point next time we talk about it. And you just pick out those order differences and you have confidence interval. And then if you take the length of that and modify it, you're going to end this here. So that will all be the same. We'll talk about that at the beginning of the period next time. Okay? So there's no quiz on Thursday, right? I do have an assignment, but I'll wait until Thursday, I'll just make it. But you'll get the assignment on Thursday.
Oh, okay. You do that.
Actually, I was going to give it today, we can do next Thursday. I'll do it on Thursday, and then, I would hope to try to get it in before spring break. You might do something on this spring break like that. You'll probably snow.